This video is to show us how to do problem 2 on the energy conservation with a rubber band. So again, just like we did on problem 1, all the energy in has to equal all the energy out. So I have an old inner tube. I actually can remember doing this when I was a little kid. We didn't have video games. You take an inner tube, you cut it, and you attach it to something that looks like this. Here's the problem they're talking about. You kind of make and you connect the inner tube there and there with a nail or something, and you pull this back and you stretch it, and then you put some kind of clothespin or something that can hold it, and you have a trigger now, and you put rocks there, and then you break something and get in trouble. But anyway, that's what we used to do. So this inner tube is going to act like a spring. And again, it's the same problem we did in number 1. That's the force, that's the distance. So the force of the spring is equal to the spring constant times delta x. So that's 1200 equals k times 1.3, and we should be able to solve that, and k is 1200 divided by 1.3, 923. And the k would be in, I have to stop and think, well, I've never worried about the units on the k, so don't worry about it. It would be, I have to get newtons, so k would be newtons over meters. There we go. Because if I solve for it, it's newtons over meters. Okay, now I have efficiency here. That means I am going to worry about friction. Okay, so I'm going to launch this rock with this velocity. So what I'm getting, and I'm going to pull it back 0.8 meters. So the energy I put in, my spring energy, is equal to 1/2 times the k, which I know, times my delta x squared. So my potential energy in the spring is 1/2 times this k right here. So that's 923 times 0.8 squared. So that equals, I'm going to take 923 divided by 2 times 0.8 squared is 295. What I got out of it was the kinetic energy, and that's 1/2 mv squared. So that's 1/2 my mass, which is right here, 7.4, times my velocity, which is 7.6 squared. So I take 0.5 times 7.4 times 7.6 squared equals 213. I got less out than I got in. That is, in real life, always the case. In real life, that's always the case. Although they can be pretty close. In some of our labs, they were pretty close. Now, my efficiency, the basic definition, work is energy. So it's energy out, what you get out over what you get in, times 100. That's efficiency. So my percentage efficiency is what I get out, which is 213.7 over 295 times 100. So divide that by 295. So it's 72% efficient. And that's how you do problem 2.